another boundary condition for magnetic field was that, and actually n is the normal vector to this interface, normal vector. So it's tangential component. I'm sorry. So its tangential component should satisfy this boundary condition. Js is a surface current or sheath current flowing along the interface of this PEC. And also this one, magnetic flux density in PEC is 0. That means that the tangential component of this magnetic flux density should equal to the surface current. So that's why, unlike the electric field, there's only a normal component. Magnetic flux has a tangential component enclosing this PEC material. Actually, note that this contour illustrates this magnetic field. So in order for this direction to be, there's a current flowing normal component, and then current will be flowing normal to this paper. So actually, this is the direction of surface current on the interface. Okay. So again, we can see that this well-engineered, PEC, which has an infinite conductance, this material can expel all the magnetic flux density from this medium. So this is the principle of the levitation. So we have a superconductor here, and then at very low temperature, we can achieve around the almost infinite conductance. We have a permanent magnet. Then if magnet is placed next to this superconductor will expel all the magnetic flux density from this magnet, so it can be levitated. It is the underlying principle of the maglev levitation train as well, to reduce all the friction force. Okay. So are there any questions so far? Okay. Then let's move on to another topic. We're going to spend most of time this lecture to look into the power, so-called Poynting vector, and also energy conservation, which is one of important conservation laws in nature. So then let's just start from the Maxwell's equation again. We can write Faraday's law in this way. And this is the Ampere's law. Sorry. And the Gauss law. E is this electric charge, and Gauss law for magnetism. So we can see that this is the Maxwell's equation, but mathematically it is not symmetric. That's because if we compare Faraday's law, the equation 1 here, and the equation 2 has only the J term, which is source term. So, but Faraday's law doesn't have any source term, so it is mathematically not symmetric. The same thing in equation 2 and 4. Again, that's because in nature there are no magnetic charge and magnetic current. However, we're gonna learn later that we can properly engineer electric current source to make equivalent behaves like a magnetic current. So even if we don't have the real magnetic current for mathematical symmetry, and also we can engineer so that we have equivalent magnetic current. So I'm gonna put M here, magnetic current. And magnetic charge. So we have mathematically symmetric Maxwell's equation here. Then at the end of manipulation, I'm gonna manipulate this Maxwell's equation to derive the energy conservation law. So and also I would like to make a comment that actually we need to find the solution electric field and magnetic field. We have two unknown field. That means that we need to solve only 2 equations. However, we have 4 equations here. So in fact, equation 3 and 4 can be derived from equation 1 and 2 by invoking the continuity equation. Continuity equation describes the charge conservation, taking the form of like this way. Okay, so I'm gonna only deal with the first and the second equation. Again, Faraday law, but I'm gonna write these 2 equations more explicitly. Actually the subscript I means impressed source. Meaning that it does not change by interaction with environment. It's just the source. It does not change. And also in Ampere's law, we have this displacement term, but we can decompose the electric current J as a impressed source. Again, it doesn't change. And also so-called conductance current. The conductance current is induced in a conductive media by external electric field, which is governed by, again, the Ohm's law. So the function of the electric field. So what we're going to do, and also, I need to change B to H, D to E by using constitutive relation, relating B field in this way and the E field in this way. Okay, so that it's going to be mu H, and then it's going to be epsilon delta E. Okay, so then let us multiply H field to the equation 1, inner product, equation 1, then it's gonna be H inner product E across E mu H dot partial H partial T plus H dot Mi, This manipulation. Another manipulation.
Sorry, I think there are a minus sign in front of the magnetic current.
Oh, yeah, that's right. Yeah, that's a good point. Yeah. Yeah, typically it's gonna be, we usually put the minus sign ahead of the magnetic current. That's because at the end of the formulation, it looks more symmetric. Yeah, that's why we put minus sign here. Yeah, thank you. Minus sign here. Then another manipulation is going to be inner product between electric field and equation 2. And we can write in this way. Plus E dot Ji plus sigma E dot E. Okay. Then we're gonna subtract the bottom equation from the above equation. Very tiny space. So minus equation, upper equation minus the lower equation. That's what we have. Yeah, hard to see, but write down. H dot. This is the left-hand side of the resulting equation. E dot curl H field. And then we get the minus sign ahead of this bracket, so that we have mu H dot partial H partial T plus E epsilon and plus a source term which got Mi plus E dot Ji and yeah, conductance term. It looks very complicated, but yeah, just the subtract the lower equation from the upper equation. Okay, so then we're going to use the vector identity to write the left-hand side of this equation more compactly, so that we can write in this way. Divergence of the E cross H. Okay, there's a vector identity, left-hand side, and the same thing on the right-hand side here. We first consider the simplest case, meaning that we don't have any source and any conductance current, so that we have this thing, just the first two terms on the right hand side. Okay, and we can also write this each term in this way by using the product rule. I mean the partial, the time derivative of the inner product of the magnetic field should be H time, the time derivative on the first term, and plus time derivative another term, but these two terms are the same, so it's gonna be just the H dot partial H partial T. That means that it's gonna be partial T, and also this mu is not non-time varying. So we can get this mu inside of this time derivative. So time derivative of 1/2 mu h inner product of this h field. And also we know that inner product of the same vector field is going to be just square of the amplitude of this vector. Okay. In the same manner, we can derive this another term this way. 1/2 permittivity and the absolute value of the electric field squared. Okay. So again, this is no source. There's no source and there's no conduction current. Then, in order to find the physical significance, it is good to investigate their dimension or unit. For example, what was the unit of the magnetic field intensity? It's gonna be amperes per meter squared, and mu. The unit of mu permeability is the Henry per meter. So it's gonna be Henry times ampere squared meter cubic, and actually the Henry times ampere squared is joule, the unit of energy. Okay, so joule per meter cubic. That means that it represents the energy density. Okay, and also because this is energy comes from the magnetic field, so we can award a physical significance to this term as the magnetic energy density. Okay, energy density. We can also do the same thing. I mean, by inspecting the unit of this permittivity and the electric field, its unit is also joule per meter cubic, and it comes from the electric field. It represents electric energy density. Simply, we can denote in this way. A lowercase w m plus we represent again magnetic energy density and electric energy density. And what would be the left-hand side term? The unit, volt per meter, amperes per meter. So its unit is gonna be because the unit of the resulting field, volt times ampere per meter square. What was volt times ampere? That would be watt, which is the unit of power. So it's gonna be power density. Okay. Actually, this power is carried by electric field and magnetic field. So we call this electromagnetic power density. Particularly, we denote this vector as a SP, which is called the Poynting vector. Just again, the power carried by electromagnetic field. Are there any questions so far? Okay. And then, particularly, it is called the instantaneous Poynting vector. Instantaneous Poynting vector, meaning that it is the function of the space and time. This is because the electric field, from the starting point, we assume that electric field and magnetic field are a function of space and time. So the resulting power is gonna be also a function of time. So that we call instantaneous Poynting vector. And then we are very familiar with this mathematical formulation. Let's recall the charge conservation. You can write in this way. What that means is that the variation, the time variation of the charge in a certain volume, actually in this differential operator form, in their infinitesimal volume, the change of charge inside of this volume is equivalent to the divergence of current. So current flowing out of that out of the surface enclosing that box. So that charge is conserved, always conserved. Likewise, if this sum of two energy is the total energy inside infinitesimal volume, so the time variation of the total energy should be equal to the divergence of this Poynting vector, divergence of the power density flowing out of this volume. So that is represent energy conservation. Okay. Energy is instantaneously conserved. Would be better. Then let's consider more complicated case by adding source and conduction current term. Okay. So actually this was the simplest case. We only considered the field, but by adding the source term, we can write this energy conservation, also called the Poynting theorem. A more general version of Poynting theorem will include the source and conduction effect by writing this way. Magnetic energy density, electric energy density, and minus sigma electric field squared, and also minus the magnetic field times magnetic current, and electric field times electric current. Okay, so we're gonna actually, if we inspect the unit of each term, it also represents the power density, or the time variation of energy. Okay, and also because electric field is always a real value, so its square is gonna be always positive. Okay, and then the resulting term is gonna be negative. Okay. However, these two terms, if we properly have the field and the source, if the sign of field and the source are opposite, it's gonna be positive. Okay. So I'm gonna denote this term as a PD and this term as a plus PS. Okay. Then the resulting general Poynting theorem will be time variation of the total energy, the PD plus PS. We have another term here on the right hand side, PDPS. So it means that the power dissipation in conduction media. So in conduction media, electric field is converted to the current, so the power is consumed in the conductive media. And the PS actually power from the source, power pumped by source. Okay. So that it pumps the energy into the system. So this is again the generalized pointing theorem. Okay. Any questions so far? Did you already learn this pointing theorem when you are undergrad or?
Not in my experience.
Yeah, that's new to me as well.
Okay, yeah. Yeah, it's very similar to the concept when you studied the circuit theory. You were dealing with complex value. I mean, yeah, the power. What was the power delivered by voltage and the current? So we can write in this way. In this case, the power is delivered by voltage and current in a circuit, and also we have a if we have a if we assume that the circuit, I mean the copper line has some ohmic loss, then we have a dissipation loss here, and also for the energy conservation, we need to add some source power. I mean this pumped by voltage source or current source, something like that. It's a very similar concept, mathematically homomorphic, but just looks complicated is because actually in this case we are dealing with vector quantity, the field. So it looks complicated, but yeah, they're same actually, essentially same. Okay. Then let's move on to the another topic, which is Phasor Technique. Okay, we know that the Maxwell's equation is linear equation, okay. Linear system. What that means actually is that the solution. Let's say if we find the solution of electric field 1 and 2. Then its summation is going to be also the solutions of Maxwell's equation. Without loss of generality, it's going to be linear superposition. I mean, linear superposition means that we multiply the different amplitude to each solution. Then it's going to be also the solutions of Maxwell's equation. So we have learned from signal analysis that the very complicated time domain signal look very complicated. Then what we was do, we analyze the signal of the time, we analyze the time harmonic signal, okay? Time harmonic signal, which means that this signal, time harmonic signal, has only one frequency, denoted by omega. The frequency is omega. Then the this signal, time harmonic signal, look like this sinusoidal function. And then this complicated solution can be given by the linear superposition of all the time harmonic signal with a different amplitude. Okay, time harmonic signal. This is because we usually assume the system is linear. Linear time invariant. So then why we are doing this job? I mean, decompose the signal in terms of time harmonic signals only analyzing time harmonic signal, and eventually we assemble all the signal, time harmonic signal. This is because actually this time harmonic signal is proportional to the exponential j omega t. Okay, so if we do the time derivative, if we operate the time derivative onto this signal, then it can be just represented by j omega term. So differential operator can be changed by a simple multiplicative factor. So the solving system becomes very, very easy and simple. Okay, so the same thing in Maxwell's equation. Then okay. In order to do this kind of task, we have two options. One is the Phasor technique, taking the Phasor technique. And the other one is more rigorous way, but looks complicated, which is used to Fourier transformation, Fourier transform. Okay, I'm gonna show you more. I'm gonna show you the simpler method, which is Phasor technique, in this lecture. But in the lecture note, PDF lecture note, you can find the explanation in Fourier transformation. Okay, so then I can start from the Euler's formula. Euler formula, which relate exponential j alpha, which is equal to the cosine alpha. Alpha is the real, arbitrarily real value, just the j sine alpha. Okay. And then in order to get the cosine alpha, we can take just the real value of the exponential j alpha. Okay, people usually call this cosine or sine term as a sinusoidal function, and the left-hand side is often called the rotating wave. Okay. And then by using this Euler formula, we're going to derive what phasor is. So to do that, okay, let's consider arbitrarily real valued function, which is a function of the space and time. It can be a scalar function of electric field, just one component of electric field, which can be by using SOV. SOV means that separation of variable in terms of space and time. Then it's gonna be I'm gonna split this spatial term with another function v dash, and cosine omega t plus alpha. Actually, this is time harmonic field having omega frequency, time harmonic field, and the cosine omega t plus alpha, arbitrarily alpha can describe any kind of sinusoidal function. Okay, and then we can write, by using this argument, we can write this one equivalent as real value of each rotating wave term, omega t plus alpha. And we can explicitly write, move the real value, and because this term is also real value, it is equivalent to write in this way, v dash x, y, z, alpha, omega, exponential j alpha, and exponential j omega t. And then Now we are going to define this as a phasor, okay? Phasor of the V, X, Y, Z, okay? And then real value of the phasor and the exponential j omega term. We have just, we can represent any real value time harmonic V signal as a real value of the multiplication of the phasor and its rotating wave term. And then what we're gonna do next is that we're gonna use this phasor technique concept to write the instantaneous pointing vector we have seen the previous slide. And then electric field, vector quantity, function of space and time. Let's say this is the time harmonic electric field having just one frequency component. And then real value of each phasor. I mean, whenever I'm writing phasor, I'm gonna add the under bar here, which is only function of space. And also this one is the complex value. But this one is the real value. And the rotating wave term. And in the similar fashion, the magnetic field can be written by using phasor again with the rotating wave term. Yeah, the same thing for magnetic field flux density, and the same thing for electric flux density. And then if we plug this phasor representation to the Maxwell's equation, then what we have, actually, let me write down the Faraday's law here. Just the phasor times rotating wave term and the time derivative of the each phasor and the rotating wave term here. Okay. And then we can write the term on the right hand side more simply because this rotating wave is only function depending on time. So action of time derivative result in just the real value of the each phasor times j omega and the rotating wave term. Okay. So that the resulting equation does not have any time derivative term. So we can just cancel this rotating wave term. Then the eventual equation is gonna be this way, the omega. Okay, so this is the equation for us to solve the phasor of the electric field and magnetic flux density. And after we solve the phasor, the solution of phasor, we can reconstruct the original real value electric field in this way. So I'm gonna write another phasor representation of the Maxwell's equation. Time derivative is replaced by j omega, the field, and also phasor of the j. Of course, we can have the phasor representation magnetic current as well. Okay. The same thing for the Gauss law. The Gauss law for magnetism. Okay. So, any questions so far on this phasor representation? Okay. Then, by using this phasor representation, then let's look into the pointing theorem. So we have defined. We have defined this is the power, instantaneous power carried by electric field and magnetic field. And if we plug the phasor representations here, that we derived in the previous slide, then we can write more explicitly this way. Phasor and the rotating wave term times real and it's phasor, phasor and the rotating wave term. And actually, for any complex value, this is the complex value, then let's say this is consists of real value A and the imaginary value B, and then the real value of Z is gonna be A. So it can be obtained by Z plus its complex conjugate over 2. Okay, so that means that we can write this term as 1 over 2 its complex, phasor plus its complex conjugate. Complex conjugate and another complex conjugate times the same in the same fashion we have plus its conjugate. So you can do the algebra. Finally, what we have is 4 terms. Cross J with 2 omega T and E cross H complex conjugate, and rotating wave term is a different signed argument, this and this, so they are cancelled. And another term, this term also does not have rotating term due to the cancellation, and the final term is gonna be minus J 2 omega T. Okay, so then we can observe that the third term is a complex conjugate of the second term, and again the fourth term is gonna be complex conjugate of the first term. So by using this relation, you can finally write 1 over just the second and third term, real value of the E cross H plus 1 over 2 real valued E cross H rotating wave term. So it's very interesting to observe that the first term, initially our instantaneous pointing vector was a function of time, but the first term does not have time dependence, so independent of the time, independent of time. On the other hand, the second term has a time dependence here. Okay. And then what we're going to do next, we're gonna do the time averaging process. So we're gonna time averaging this instantaneous power pointing vector that can be written in this way. So meaning that we're gonna integrate this pointing vector over a certain domain from 0 to uppercase T, and then we multiply by 1 over T and then get the uppercase T go to infinite. Then this one is gonna be time averaged power, usually denoted in this way, with bracket here. So if we plug this expression that we derived to this time averaging operation, then we can figure out that the second term, due to this rotating wave term, it's gonna be rotating based on the 0 axis. So integration minus infinity to infinity is gonna be 0. So that the second term after time averaging is gonna disappear. Okay, so we only have the first term after the time averaging process. So this eventually means that time averaged power. Okay. And particularly, we can define this term. This should be phasor, and also this all should be phasor. Okay. Then we are gonna define these as a complex power. Complex power. Also called a complex pointing vector. So in order to get this time averaged power, we can only take the time averaged power. We can only take the real value of this complex power or complex pointing vector. So, so the time average, again, time averaged instantaneous power is equivalent to the real value of this complex pointing vector. Yeah. Any questions so far? Yeah. To understand this complex pointing vector, it would be better to see what happens in the circuit theory. So if we look at the left figure, okay, we have a source on the left, and we have a resistance, and also inductance on the right. Usually, we can write the current flowing along this circuit as a voltage versus impedance. Impedance is gonna be R plus J omega R. And actually, it is the phasor. Okay. And then we can write the power, complex power flowing through this circuit. It's gonna be voltage times current. So the time average power is gonna be one of the real value of this complex. So that's the same to the electromagnetic field. Okay. But let me make a comment for then what is the physical meaning of the imaginary component of this complex power. Okay. So it's also more intuitive to observe what happens in circuit theory. If we do not have the inductance, which is proportional, of which the impedance is proportional to J omega, then we can describe the power flowing through the circuit through the figure on the top. Actually, this illustrates the time versus its time varying instantaneous power. So the power is always positive based on the 1 over P naught. It's gonna be time averaged power. The power is strong based on this time averaged. So because power is positive, that means that this resistance always consumes the power. That power is pumped by a voltage source. On the other hand, if we have inductance, so that the phase between the voltage and current has out of phase or phase delay, then if we calculate the complex power, and then from the complex power, if we calculate the instantaneous power, over some time it takes the positive value, but it can also take the negative value. Then what would be the physical meaning of the negative power? You know that from the circuit theory, the negative power is the power flowing from the load to source, not from source to load. Okay, so that and also this negative instantaneous power result from the imaginary component of the complex power. Okay, it's called the reactive power. So again, the imaginary component of this complex power physically means the power flowing from the medium to source. Okay. So any questions so far?
So what is A in the figure?
A in a figure?
Right.
What is A? You mean this A?
Oh, sorry, alpha.
R. Where's R?
Alpha. Okay. That's the one you.
Let me see. So you mean R bar?
Alpha.
Alpha. Yeah, I'm sorry.
Sorry.
Alpha is kind of degree of the circuit being. Alpha is the kind of phase relative phase difference between voltage and current. Okay, so for example, if we have only inductance, then the voltage is gonna be current times Z, and because Z is J omega L, so that if we assume that this current has just a zero phase, then the voltage would have 90-degree phase delay from this. Due to this inductance J term. So in that case, this alpha is again just relative phase difference between voltage and current. That means that we usually call the inductance and capacitance as a reactive term. So in a circuit, if we don't have any reactive term, then there's no phase delay between voltage and current. So in this figure, this alpha 0 describes that situation. And in that case, we don't have a negative power, but if the alpha is non-zero, meaning that we have a reactive component in the circuit, then voltage and current has a relative phase difference, and so that we have a negative value power. Again, that power is flowing from load to source.
Okay, thanks.
Any other questions?
Yes, I have one. What is the physical meaning of the power of the current flowing from the load to the source? How does it happen?
Yeah, that's very good question. For example, later you are going to study about the radiation from source. So we have a current source. Let's say we have a point current source, then it radiates electromagnetic field. And actually this point source can be antenna in your cell phone, any kind of sources can be a model. It oversimplified, but we can use the point source. But if this point source has very poor efficiency, the radiation efficiency. Let's say the point source wanted to radiate the 100 amount of energy through the electromagnetic field, but point source has again the poor radiation efficiency. The field is gonna not gonna radiate, but it just exists in the vicinity of the point source. And actually that power radiated and back to the source describes this kind of imaginary component of the pointing vector. Okay, we call this as a near field. Those kind of power flowing back and forth near point source and back to point source. And only the time averaging, the real part of the complex value is going to describe the radiating field from this point source. Okay. Was that enough, or maybe?
Yeah, I think that explains. Thanks. And I have similar question on the physical meaning of imaginary part of pointing vector.
Mhm.
And basically, why don't we use the sine instead of cosine when considering Phasor technique?
You mean,
Well, those are two separate questions. Let it be
yeah,
separate
okay.
questions.
You mean referring this equation?
Yeah, when we consider
Mhm.
the field being time harmonic, we
Mhm.
consider it to follow the cosine law, like going along the cosine. Why not the sine?
Yeah, actually it takes the form of cosine, but due to the fact that we add another arbitrarily factor alpha, yes, summed with omega t, so it can be, depending on the alpha, it can be, yeah, a sine function as well. For example, let's say maybe better. Can you very tiny thing, but let's say this is cosine function, cosine omega t. But by choosing, for example, if we choose the alpha as a 90-degree or pi over 2, uh, then it means that just um, translate that cosine function. Okay, this is gonna be cosine omega t plus alpha, very small, but it is equivalently the sine omega t. I'm not sure the sine, but by choosing alpha, then we can make this cosine to the sine function. And in the phasor, the reason that the phasor is complex valued, actually we decompose this omega and alpha separately, and then we incorporate this alpha term into the phasor so that the phasor itself will takes into account this translation effect. So because we are adding this arbitrarily alpha term inside the cosine function, we can say that we are already considering, yeah, cosine and sine any function.
Okay, thanks. And another question, yeah, that on the imaginary part of the power of the pointing vector.
Yep.
Yeah, what's the physical meaning of the imaginary part of this complex pointing vector?
Mm-hmm. Yeah. So the physical meaning of the real valued complex value is the time averaging power consumed in media. Okay. So in this electromagnetic case, that consumed power takes the form of the electromagnetic field. It can be radiating or it can be exist inside some cavity. Anyhow, that power takes the form of the field. Okay, and that power originally comes from some source, some kind of source. Okay, but the imaginary part is usually called reactive power. The power is conveyed from fields to source. Again, um, that is that can be seen in this example, the radiating situation. The radiate, actually, it's not radiate, just it's the field are generated from this point source, but it's not gonna radiate. But as time evolves, it gets back to the source. So the field disappears and the energy is absorbed to the source. So that is the physical meaning of the imaginary part of this complex power.
Okay, I see. Thank you.
Mhm. I think we are now, we can stop here just because 2:45. Yeah, thank you everyone. And if you have any questions, you can email TAs or me or Professor Chu. Any questions are welcome. Yeah, thank you very much.
Thank you.
Thank you for your time.
Thank you.
Thank you.
Thank you.
Thank you for time.
Thank you.